from University of Sydney, Australia. So many of you know Tarak, but this will give an introduction. Tarak did his PhD from IIT Kharagpur. He did a postdoc here for 2 years. And then this period he was also postdoc at HRI, that's waiting for the student visa. And then he's a postdoc now at University of Sydney, studying more. So Tarak has worked on a variety of topics in BS and physics. In particular, he has worked on all three frontiers of dark matter: model building, reaction, and integration. Nowadays, he also getting a lot of interest in world-leading work on neutrinos and reaction. Then he tells us this talk based on these two papers, how we can use neutrinos as a friend or a foe for doing physics. Thank you.
Okay, that is probably one of the nicest introductions that I got to my life. Let's title this. Okay, so I'd like to thank you all for coming to my talk, and special thanks to Ranjan for arranging this. So I'll be talking about neutrinos at direct detection. So as you know, in direct detection, what essentially we look for is dark matter interaction with standard model state. So if you want to search for very small dark matter standard model interaction, the neutrino would be an important background to the searches. So in first half of my talk, what I'll be talking about is how neutrino could slow down the search of the sub-GeV dark matter electron scattering. And in latter part of my talk, what I'm going to talk about is how the detection of neutrinos with current detectors like XENONNT and PandaX could help you to measure a standard model parameter, perhaps at the lowest energy scale. So in particular, the standard model parameter that we could measure is the weak mixing angle. So this talk would be primarily based on these two papers. So this is sort of the plan. I've told it briefly. So essentially, we try to look for dark matter. We put some detector at underground so that we get rid of other background like cosmic rays. And our expectation is that dark matter comes, hit the detector, produce some recoil, and you try to observe it. Now, if you try to search for small enough dark matter standard model cross section, typically what happens is that, or at least in our case, solar neutrinos are an important background. So this is sort of and being in background, they sort of produce dark matter like signature and slow down the search of the dark matter. This is sort of first part of my talk. In the latter part, what I am going to show you is that with current detection of the neutrinos at direct detection experiments like XENONNT and PandaX, we could measure weak mixing angle perhaps at the lowest energy scale utilizing neutrino electron scattering. So this is sort of a traditional side, dark matter exists, and evidence comes from various different astrophysical and cosmological length scale. The problem with dark matter is not about it actually fits various astrophysical and cosmological observation very well. The problem with dark matter is standard model doesn't have any candidate for the dark matter. So you need to find some BHF physics which could explain the, let's say, dark matter, the 27% of the energy budget of the universe. We know very little about it, like it has to be stable, it has to be either absolutely stable or maybe very long lived, like the lifetime which is larger than the age of the universe. It has to be cold because of the structure formation says this, in the sense that it must move with velocities which is smaller than the velocity of the light, and it has to be massive because that's how we get to know about it. So diabetes is the only thing that so we should get to know about it. And the allowed mass range is almost probably 90 orders of magnitude is allowed. Now, given it has mass, what else it could have? We don't know what else it could have. We want to know it. Now, to characterize dark matter, what you have to do is test every possible interaction. Since we don't know what it couples to, you have to probably test every possible interaction. And if you are lucky enough, then probably you discover it and book a ticket for Stockholm. And if you are not, then set some bounds on the dark matter parameter space. With that in aim, what we are going to focus on is dark matter electron scattering. So essentially what we'll try to do over here is that we'll try to, so the idea here is that you have a detector on underground material, dark matter comes, hit the electron of the target material, produce some recoil, and it will try to observe that particular recoil. Now put the things in perspective, what I am showing you here is the energy content within a dark matter. So as I said, I'll be interested in dark matter which are of masses less than the proton mass, sub-GeV scale. So that's why I sort of put the number in that regime itself. So if you have dark matter mass, which let's say hundreds of MeV, and you know typical dark matter velocities in natural limit is 10 power minus 3 C. So the energy content is within about 50 eV or so. So now if you have 50 eV energy, even if you let's say through elastic dark matter elastic dark matter electron scattering, if you transfer even a fraction of it, what you could do is you could ionize the electron from the atomic state, because your atomic ionization energy is around 10 eV or so. Or you can transfer electron from the valence band to conduction band too. So now in an like proper theoretical calculation, what you need to take into account, what is the ionization probability and what is the how much of the energy that you are transferring given the elastic scattering. We do take into account all these things, but the idea that I'm sort of trying to give here is that you could in principle observe dark matter electron scattering utilizing this phenomenon. Okay. Now given this, are the experiments capable enough to observe this thing? So I will mostly be focusing on these two type of experiments, these two type of popular experiments which are sort of setting the leading bounds in the dark matter diameter space. So one is xenon target experiments, other one is semiconductor target experiments. So in typical xenon two-phase time projection chamber, the detector of the typical two-phase time projection chamber looks like this. So this is the pattern picture for that. So the yellow color region is.
So in the previous slide we showed the interaction of dark matter and electrons.
Yeah.
What kind of interaction should it be?
So
What kind of interaction?
So this is the sort of thing that I'm interested in. So this is just the elastic scattering between dark matter and electron.
Just a photon interaction.
Or even it could be mediated by a particle too.
But in this talk, I think it's sort of modeling effect. It just wants the
So you could have something like, let's say, this electron, and you could have mediator and. So I'd not be talking about any particular model, but there are some sort of model assumption there which I can be discussing as we go on.
mostly we use the kinematics. It can appear by the artificial also. Typically also in like
Okay, so this is how your xenon two-phase time projection looks like. You have two phase in the sense that you have both liquid and gas of xenon. So the yellow color region is the liquid xenon thing, which is the main target for the xenon material. And we have this gray color thing that is both top and bottom, which are the photomultiplier tubes, and we have also electric field applying this direction. So if you have any energy deposition in this kind of material, which is mostly going to be in the liquid xenon part, that is going to produce some heat. This experiment just cannot observe that heat. It is also going to produce some excitation, which is essentially producing this excimer of xenon, and which essentially gives you this particular kind of scintillation light. And this you observe promptly, and experimentally is called as S1. This you can observe both upper and lower PMTs, mostly in the lower PMTs, but you are also going to observe in the lower upper PMTs too. So this experimental is called as S1. So you are going to produce some excitation, experiment observe it, they are calling it as S1. Now along with excitation, you are also going to produce some ionization, and due to this electric field, some of the electrons are going to be drifted upwards, and you can observe again proportional scintillation signature, which experimentally is called as S2. Right. Now depending on what kind of interaction is producing this S1 and S2, the topology of the S1 and S2 really looks very different. For instance, if you have electron recoil, then you are predominantly going to produce more ionization compared to excitation. So that's why the strength of the S2, which is essentially determined by how many electrons are sort of been pushed upward direction by the electric field, would be larger compared to the excitation. So that's why the S2 strength would be larger compared to S1. So essentially, if you want to separate out what is nuclear and electron recoil, what you need to focus on is the ratio between S1 and S2. And above half a keV energy, like if your recoil energy is above half a keV or so, you could separate out between nuclear and electron recoil very efficiently. Now if your recoil energy falls below half a keV or so, then you cannot observe S1 because it's really very small, and you could observe still S2 because the ionization that you are producing could be accelerated because of the electric field, and you can observe the S2. And that's why, because of, to search for such low energy recoil, people usually focuses on S2 only analysis. And as I was talking about dark matter mass, which are of sub-GeV regime, the energy content within those particles are really very small. That's why you need to sort of sub-GeV dark matter searches are typically focuses on in the S2 only analysis.
Nowadays I've seen at least one xenon paper
So for
For electron recoil structure.
so typically that would be around above 1 keV or so. So that electron recoil has to be above 1 keV or so. And if you have typical scattering between, let's say, elastic scattering between dark matter electron, producing 1 keV recoil is a bit difficult, but you can produce it with suppressed rate. S2 pulse? Yeah. It depends on what kind of interaction is producing this. So this ratio is roughly around 1, as you can see from this plot. For nuclear recoil, even could be larger than that, but for electron recoils, it's probably like orders of magnitude larger than the this one. So it depends on what kind of interaction. Yeah, I am talking about amplitude. So for nuclear recoil, so width of the pulse, this width that you are talking. Oh, okay. That depends on actually at where the interaction is happening also. Like if you have interaction happening, let's say at the bottom of these things, then it sort of be diffuse, then the width would be changed. So it depends on various different. These are just schematic. Don't take it very seriously. Okay. Okay. So essentially, the point over here is that if you do this S2 analysis, while you could do dark matter searches, but your experiment lose the capability to separate between nuclear and electron recoil, because you just cannot measure it, so you don't have the ratio of this S2 and S1, your experiment just cannot separate it.
So, what is the you have the time axis?
Yeah.
Clearly, the width of S2 and S1 is decided based on time.
No, not based on time. It also depends on where the interaction is happening. So if the interaction happens, let's say somewhere in between, in the middle, then the diffuse time would be small. I mean, probably in the middle range. Then the width would be something different from what is happening. Let's say if interaction happens at top of the things. So diffuse time sort of sets the what is the width of the thing. Diffuse time is the only one parameter which sets the width of the things. There are many other parameters which could also, like what is the sort of for the S2, what if there is any impurity in the material, the electron would also recombine with the impurities of the material, and then the S2 will also change.
If there's an interaction that happens way up there,
But in this
effective time for the
in this kind of thing, you can also measure at where the interaction is happening.
Yeah, you can. So, I mean, all I'm saying is, in principle, what can happen is that the S1 and S2 can, in principle, that's probably unlikely, they can actually overlap. You may not be able
Right,
to make
right.
it
If
If there, right, because you have the feature that is there.
no, that let's say some interaction which is happening exactly at the top.
So,
So there's not
up
much
there,
volume.
so the effective
Sorry?
time
Not much volume there.
No, what I'm saying is exactly at the exactly somewhere over here. Then it can happen actually. But typical difference between this S1 and S2 time is around 100 milliseconds or so.
That's the end of the I mean, in the end, you probably have to do an average of what you know, because it's a counting experiment. Yeah, right? So
For each, I mean, if your recoil energy is, let's say, above half a keV or so, for each of the interaction you can reconstruct where your interaction is happening. Right? Okay. Other than this, as I said, people do also use semiconductor target. In semiconductor target, what people usually use is CCD as a target material. CCDs are there in the smartphone too. And you do observe various different astrophysical objects using CCDs, and each of these CCDs contain millions of pixels, and each of these pixels has, let's say, silicon as a target material. Now, if dark matter deposits some energy, it could transfer electron from the valence band to conduction band, essentially producing electron hole pair. Now, depending on what you are interested in and what you can measure in your experiment, either you measure electron or hole. Typically, sensei like experiment measure hole. Now, given this, so let's say you have produced some either electron or hole in one of these experiments. So let's say this is my CCD. It has again, this is a schematic figure. So this is my CCD. It has this many number of pixels, and I have assumed that I have produced charge in these 3 pixels. This is just an assumption. You could produce somewhere else too. Now, if you really want to read out these particular charges, what you have to do is you have to move these charges vertically downwards. This particular pixel, the charge moves vertically downward. Then again in the horizontal direction, this is essentially just applying the voltage differences. We apply voltage difference and kept on moving the charges, and finally we read out in some readout strategy. Now this is how your typical CCDs work. For the sensei and dummy, what they use is called skipper CCD. What they do is they measure each of this pixel hundreds of times. So as you know, so any pixel. So they measure each of this pixel hundreds of times. So that means, as you know, in any measurement, if you measure it more times, you actually reduce the noise of your measurement. That's what they try to do. This is very simple. So if you, so what they usually do is they measure it probably around 300 times or so, and they reduce the noise of the measurement to a sub-electron level. So essentially, this is how your dynamic or sensei-like experiments operates.
So for which cases the semiconductor, these things are preferred over the xenon?
So that I'll be coming in the probably slide after this. Okay, now here also we do not have a handle to separate out between nuclear and electron recoil. This is I'm mentioning this because this is important for the latter topic. All these experiments have tried to search for, let's say, dark matter electron interaction. They have not found any excess. That leads to the bounds in the dark matter parameter space. This is again schematic figure. What have been plotted in the x-axis is the energy, y-axis is the number of events.
Sensei only shows dark matter electron spectrum.
They-
And then you proton by the meter.
Right. Right. Yeah. Okay. Now all these black points that you could see over here are the observed things that in your experiments, the observed number of events in your experiment, and blue solid line is, let's say, expectation from the background with the shaded region is the uncertainty in the background measurement.
After all excesses were resolved,
This is after,
all spurious excesses were resolved.
right. This is after separating out.
Resolution of excesses has been, not all of them have been done.
So I mean, there is one more excess. You can check this paper. This is by Damik and Sensei. They have some excess in the lower energies. They do not understand where it is coming from. But
Dark matter, because you can show that they don't scale up with the size of X. That's a trivial thing.
Okay, I see.
It is not dark matter. It
So
must
some
be-
of
Must
this,
be system or
like
There is-
some.
Or it works up on excess, where they talk about.
So that's what I said.
So what happens is that-
after the excesses workshop has determined.
No, so they do not know what is
Yeah, so they don't
excess,
know.
but definitely not dark matter. This is the.
So that, I mean, one of the reasons that could produce this kind of like exposure independent thing is that while you are reading the things, you are essentially applying some voltage differences between the pixel, and that could see some spurious charge and spurious hole that could sort of be appear over here.
Some point I heard that one of the things was it was also holding the crystals.
Right, yeah. Right. Even for let's say PandaX-4T analysis for HB neutrino searches, there are this background called cathode, which are basically cathode are producing beta decays and producing this kind of thing. Okay, so essentially the point over here is that it is roughly consistent with the data, and if you put a signal which has a strength looks like this red solid line by eye, you could see that it is not consistent with the data because it is overshooting the observation in these first few events. Now if you kept on decreasing the strength of your signal which are coming from, let's say, dark matter, then at some point it would be statistically consistent with the data, and that sort of leads to the bounce in the dark matter parameter space. This is what it bounce looks like. Again, dark matter mass is on the x-axis, cross-section in the y-axis. In the small masses, your equal energy is not large enough so that you can observe it in your experiments. At higher masses, it's sort of linearly increasing. The sensitivity is falling because the number of events that you could observe in your experiments depends on how many dark matter particles are hitting your detector. That depends on what is the energy density of the dark matter, local energy density after you know, and it is inversely proportional to the mass of the dark matter. So as the mass increases, the rate is decreasing. That's why the cross section that you could probe is rather large. So sensitivity is also decreasing. This is again schematic. Now comes to the realistic plot. So what have been plotted for both of these plot is dark matter mass in the x-axis, dark matter electron interaction cross section in the y-axis. Left one is for the case where heavy mediator is mediating the interaction between dark matter electron, heavier than dark matter mass, and right one is for the case where dark matter electron interaction is mediated by a particle which is smaller than the dark matter mass. I don't want to read each of these black solid line or gray solid line over here. What I really want you to focus on is the envelope of this gray solid thing. What it essentially suggests is that direct detection experiments are ruling out anything above that particular cross section up to a certain cross section by these kind of experiments. And to answer your question, you see this dynamic and other things uses silicon, and they are important over here. They are setting the leading bounds below about 10 MeV or so. Okay, so now all this plot has ceiling. That is because if you have large interaction cross section, then dark matter will just not reach your detector. For instance, if a xenon detector is around 1.5 kilometer at a depth of 1.5 kilometer, so it would interact with the electrons which are in the crust and sort of loses energy, so that you cannot observe this thing.
What happened to CDMS silicon?
CDMS?
Silicon, they never reported results?
CDMS result is just one.
Oh, sorry, I couldn't see that.
Sorry. Okay. Now the question that we have asked is, in this parameter space, where do neutrinos are? That means at what particular dark matter electron scattering cross section neutrino would be an important background to researchers. So to do that, you need to know what are the source of these neutrinos. These are essentially coming from the sun. You know, different solar nuclear reaction chain are producing neutrinos. Here is a sort of a plot for that. In the y-axis is the neutrino energy. X-axis is the neutrino energy. Y-axis is how many of those neutrinos are hitting per centimeter squared per unit energy, per unit area, and per unit time. This different labeling are just sort of in proxy for different nuclear reaction chain, and solid line is the red solid and dashed line are the fluxes that you are expecting from this sort of reaction. Now, what this neutrino could do is, this neutrino comes and hit your detector through this kind of reaction and produce a recoil which could mimic dark matter reaction. So essentially, through coherent elastic neutrino nuclear scattering, it could produce a dark matter like signature. Now you may ask, so far you have been talking about dark matter electron scattering, then why do we bother about coherent neutrino nuclear scattering? That is just because I said these experiments, the energy regime where they are searching for this sub-GeV dark matter electron scattering, they could not separate out what is nuclear recoil, what is electron recoil. That's why you need to focus on coherent neutrino nuclear scattering. There could be some contamination from neutrino electron scattering too, but the cross section itself is small, so the contribution would be small. Sorry, it really doesn't matter here. So yeah, essentially the ionization that you are producing from the nuclear recoil will show up as an electron. So then what you have to do is, you have to calculate the event rate against energy. So what is the typical plot for liquid xenon and silicon? X-axis is sort of a proxy for number of electrons, which is, you can sort of take it as a recoil energy.
So in neutrino nuclear recoil, how am I getting S2?
Now am I?
How am I getting the S2?
So essentially you are recoiling the nucleus, and that let's say you are recoiling the atom, and that atom interact with the, let's say, atom which is just near to it, and because of the Coulomb interaction they could produce a Okay, so essentially you calculate the number of events against the recoil energy, number of electrons is a sort of a proxy for that, and here is a sort of a number for few benchmark choices of the dark matter and neutrinos. So dash line is for the case where 8B solar neutrinos are contributing, sorry, dash line is for the case where neutrinos contribution are taken into account, and solid line is for the cases where dark matter, different choices of the dark matter is taken into account. Now given this, what essentially you need to look at is this kind of plot to get the cross section at which neutrino would become an important background. So what have been plotted in the
So the shape is always very different.
right, it's always different. Like for the nuclear recoil case,
So
five,
that is dark electron scale.
right.
That is these examples.
They are not really, yeah, yeah,
Different.
yeah. That's the point.
really important.
Yeah.
So it's coherent on all the 9 or 10 number of electrons.
Sorry.
It's coherent, right? Or
Yeah.
This current scattering
Yeah,
cross
I mean 9 you can, I mean the number of electrons here is just a proxy for recoil energy. If it is 1 electron, then you can think it of as just producing, let's say, ionized electron from the outside of the cell. This is just,
Right.
this is just let's say 11 or 10 eV or so.
So how did they compute this?
I mean number of electrons.
No, yeah, yeah. How did they compute this cross section?
Sorry.
Rate.
Right. So essentially, in calculating cross section, you need to take into account what is the ionization probability given a recoil energy,
Right.
and what is the dark matter electron return cross section, what is the dark matter velocity distribution. You need to take those into account. Then you need to calculate it.
Only
Now,
one number, how do you get precisely the number of electrons? That's the, what is the modeling you do?
oh, okay. So that I think I cannot say it right now. There is a bit like several different difficult things that appear over there. But for silicon, it's just, let's say, once you produce a recoil energy which is above your band gap, then you are going to produce 1 electron. Now, yeah, yeah. Now there is some mean energy for which you can get another 1 electron. So once you cross that particular mean energy, then you are going to produce 1 more electron. There's something like that. Right. You do,
You're not calculating a squared matrix element.
right. That I do think.
Just looking at the shape. I mean, there will be some form factor.
So ionization probability itself is, I mean, okay, this business has started from, let's say, 2012 or so. Now people have tried to modify this ionization form factor depending on like where the relativistic effect could be important, where the atomic effects could be important. These people have tried to calculate take these things into account in the calculation.
So at this level, it's still phenomenological process. A cross section is from. This is first model. There's no model. This is not a first principle.
No. This is just a numbers, sort of a number.
The dark matter and neutrinos have similar number of electronic shape, but the rate shape for the silicon case or the semiconductor case is different, right?
So it depends on various different things. One of the important thing over here is for xenon the ionization energy 10 eV, and for semiconductor band gap is around 1 eV or so. That's sort of one thing which is different. Now since it is 10 eV ionization energy, then you are sensitive to certain portion of the solar neutrino fluxes for xenon, but for let's say semiconductor you are sensitive to the even lower energy neutrino fluxes. So that's why even if it is similar exposure, you are getting more events. So these are the things that are determining that. Okay. Now in this plot, what have been plotted is the exposure in the x-axis, and given exposure, what is the minimum cross section that you could probe in your experiment is given in the y-axis. So exposure is sort of, when let's say if you have 10 kg exposure, that means you have 10 kg of experiment which is keeping you have kept it for, let's say, or your experiment is running it for 1 year. That's what 10 kg means. Now you can scale it for the other two. Now the blue solid line that you could see over here is what we are getting from the numerical calculation, and dashed line are sort of an indicative representation of those particular lines. So at the lowest exposure, this is a bit technical. So at the lowest exposure, your experiment is not seeing any neutrino events, so that's why it's sort of in background free searches. As you kept on increasing your exposure, it's entering the statistical uncertainty dominated regime, and as you kept on increasing your exposure further, it would enter in a systematic uncertainty dominated regime, where you are producing your dark matter events are producing less than what could be produced by background fluctuation from the neutrinos. So we do not know the neutrino flux very precisely. We do know these things with good accuracy, but we do not know it very precisely. That's why you enter in the systematic uncertainty. This is from our numerical. So this dashed line,
So the dashed line is the
sort of an indicative behavior of this particular process.
solid line.
Solid line is from our calculation itself. Okay, now if you increase the exposure
So
for
let me go back to the question about calculating cross section itself. So there must be uncertainty in the calculation of cross section.
so we do not
There
take
should be
no, we do not take into account those uncertainties. We only take into account uncertainties that are coming from the neutrino fluxes.
That is the form factor.
No, what he is saying is,
Which
let's say you have dark matter electron interaction,
Oh, yeah.
then do you know precisely what is
Oh,
the
yeah,
event
there
rate?
is a
Yeah.
point and dependent on
Okay.
the- So this is
So no. Even beyond that, I mean, different people will give you different ionization probability.
That's my point, because I've seen this plot.
Right.
I have heard arguments about what.
Right. That we do not take into account in this calculation.
Who is producing this?
Right. That I do not take. But we are sort of being state of the art with the rate calculation. Whatever we know, at least around that. Yeah.
The reason you are not taking into account is because the uncertainty is much smaller than the.
That we don't know. For some of the let's say single electron beam analysis, it could be even larger than that. And also for some masses too, it could be. It's just because of the ionization probability is not really known with 3D, and you do not have measurements over there.
Yes, some major effect, but no, some not at those scale.
Not at those energy scale. Yeah. Okay. And if you increase your exposure further, your experiment can measure its own background and you can just separate out dark matter and neutrino utilizing, let's say, tail of your distribution. Here, I mean, they are not. If the dark matter and neutrino share identical spectrum, then this flat line would have gone on even if your exposure is infinite. But your dark matter and neutrino, as I shown earlier, is not sharing identical spectrum. You could separate out those utilizing when you use exposure. So essentially, the point over here is that there is no hard floor in the cross section. You can theoretically, in principle, probe any cross section you want, but practically, you need probably interval xenons or interval silicon to probe this kind of process. Practically, those are perhaps impossible. So that's why people sort of, instead of calling it as a neutrino float, people sort of calling it as nowadays neutrino fog. Now, given this, so then what you may ask is, can you give me a visual guide to the cross section which could sort of give us an indication that neutrino would become an important background. To do that, we have followed the prescription of this particular paper, essentially calculating the gradient of this particular line, gradient of this blue solid line, and once you try to calculate the gradient at background free regime, it is roughly around 1, and in this Poisson regime or statistical uncertainty dominated regime, it is 2, and once you cross the statistical to systematic uncertainty dominated regime, it's become greater than equals to 2, greater than 2. So
There is a particular point in this exposure where this this systematic uncertainty starts to dominate. So that depends on the model.
systematic uncertainty, that actually depends on the uncertainty of the neutrino fluxes. And since for, let's say, different target, different sort of solar neutrinos are contributing, so it would depends on that particular, whatever neutrino fluxes is dominantly contributing, uncertainty of that particular neutrino flux will dominate over there. Okay, so now as you understand, over here in the systematic uncertainty dominated regime, even if you are increasing the exposure by orders of magnitude, but the cross section that you are probing is really very small. So you are increasing your exposure by orders of magnitude, but the change in the cross section is by only 1 order of magnitude. So essentially what I am saying is that once you enter in the systematic uncertainty dominated regime, probing those cross sections is really very difficult. So you can sort of define statistical and systematic uncertainty dominated regime boundary as a sort of visual guide to the neutrino. That's what we try to do, and this is what our calculation. So below this cross section, below this particular black solid line, your dark matter electron scattering, or the surface for the dark matter electron scattering even enters in the systematic uncertainty dominated regime, and anything below this cross section is, you can call it as a neutrino fog, and probably perhaps this cross section is sort of a visual guide to the neutrino fog. And you could do this is for a particular mass of the dark matter, particular interaction, particular target. You could do this for various different target and various different masses. Here is our plot. So even if you don't get anything from this talk, so what I'm showing over here is, again, dark matter mass is on the x-axis, dark matter electron scattering cross section on the y-axis. This gray region as already I discussed. So even if you don't get anything in the plot, anything from my talk, what I want you to focus on is this particular line. So if your dark matter electron scattering cross section lies below this particular line, your neutrino solar neutrino would become an important background to research. Now,
What's the shading in this?
so shaded region is sort of if you have more spectral degeneracy, then you have, so essentially it is map in the gradient of the neutrino, gradient of the particular line. So it's the gradient being map over here. So in this regime, let's say at this cross section, your gradients becomes greater than 2 and it is larger. So those dark shaded region represents those kind of cross section. So essentially the regime where you are in the systematic uncertainty dominated regime.
One question. So here we are considering this dark matter electron will be our point diagram.
Mhm.
So here the electron is free, right? We are considering that this
No. So you do take into account atomic effects over there. Okay. So then this is the similarist thing for xenon target 2, which is shown over by this green solid line. Now one may ask, why do you care about this kind of cross section? Probably the
The xenon thing, that is the flow.
right.
Why did you go to the mass?
Because if you have dark matter masses which is below this one, then the available recoil energy is not greater than the ionization energy of the outer shell of the xenon. So the xenon outer shell energy is around 11 eV, so you do not have that much of energy.
So that's like a hard cover.
Yeah. So it could be, let's say,
Yeah, no, right.
yeah. Okay, the next thing is, why do we should
But
care?
that will be different from argon, because argon is less.
Right.
Very good.
So we care about this kind of cross section because probably the nicest answer is any dark matter electron allowed cross section should be searched for, because we don't know what it couples to. So that's why we should care about every cross section. Now again, to sort of guide you, here is sort of a regime for the theory targets, where some of the models could produce the correct rel intensity with different sort of mechanism. So for this lower dark matter masses, which is around 1 MeV or 10 MeV, their neutrino flows is really far apart, but around 100 MeV it's really very close. Like it's in the regime of the neutrino flow.
So the silicon thing, I understand this. For xenon, why is there this curve?
So I can show you plot later.
Okay, we can know.
Yeah. So that was current while we are doing this plot. I think this has improved a lot after the atomic energy. But for this would be better for the light mediator thing, because light mediator you have 1 by q square and your momentum transfer is small, so that's why you have large portion of the rate is sort of in lowest energy spin, and that you can observe in lowest threshold experiment, which is Dramik and Sensor. So I don't know people have calculated it for. I don't know whether people have calculated for that. We are not calculating. No, I don't know whether people have calculated that. Yeah. Right. That's what. Right. Okay. So far what I have been talking is, you can detect these neutrinos in dark matter experiment, which would be problematic to the dark matter searches. And the next question that we have asked is, given that we can detect these neutrinos, can you say something new, or can you do some novel physics with those detections? So particularly what we are interested in testing a standard model parameter, which is weak mixing angle, as you know. So this is a mixing between third component of the SU2L gauge boson and U1Y, which gives rise to physical photon and G boson. And essentially theta W is what is.
Can I
Yeah.
understand completely? So your claim is that only the neutrino flow, all the background can be understood just from solar neutrinos?
Yeah, they are all the backgrounds that are coming from
Nothing
solar
else.
neutrinos, nothing else.
The neutrino flow essentially consists of
Solar neutrinos,
and
yeah.
now if you can detect them, you are done. essentially.
If you can understand them better, then you will probably can get rid of that. But understanding that requires the exposure, which is probably
course, that's
impractical.
right.
Impractical.
In some sense, when you ever reach those stages, something like hypertension will already be running, right? And you should probably improve at least the boron 8.
Right, you could
Or
reduce the
you-
uncertainty of the flux. Probably you could go down in the, once you reduce the uncertainty.
Because when you go in this thing, you are assuming the dark matter itself is measuring the flux, right? Go to the thing last, when it starts to fall. Yeah, when you are in that regime where it starts to fall again after the system is, you are assuming that it's the dark matter which is informing you about the solar neutrino flux uncertainty. But one can also input what we done from Juno.
Right. You
or
can do
whatever
that.
it
Then
is.
essentially
It
the
will shift like this, right?
yeah, it would be shifted something like this.
Yes.
So this crossing would happen at smaller cross section.
Small exposure.
Smaller cross section. Because I mean,
Anyway,
yeah.
okay.
So what I'm trying to say is that here you enter in the systematic uncertainty dominated regime.
Yes.
If your systematic uncertainty is small, then this line will probably be
Yes,
flat.
that's what, if I use neutrino experiments to decrease the systematic.
Right. You could in principle do that. Whatever we are doing is sort of a current based knowledge,
You know that.
either from standard solar model or from the detection.
Is anybody in solar neutron community looked at how to measure they must?
There are papers like even with XLCD people are trying to how much, but or with Darwin how much better you could measure it.
How well we
That I don't know.
measure the boron flux, or you know.
There should be. Okay, so the theta w itself is the mixing angle, but usually it's sin square theta w in the literature, which is called as mixing angle. That's what I am also going to do so. And sin square theta w related to gauge coupling through the relation at tree level. Once you take into account correction, that would lead to the running of the coupling, and that sort of gives you this kind of plot. So again, sin square theta w is plotted against the energy scale. The blue solid line is what you are expecting from the standard model, and different observation essentially utilizing the weak processes in the standard model is sort of given you by these different sort of points in black points over the plot. Out of these, the lowest one is by atomic parity violation experiments. Sorry? You see, LHC is not an anomaly. This is just
we won't
we are also confused when
we got confused.
So who made this plot?
this is from PDG. Okay.
Fitting group. They made this plot. This is a disaster. This plot.
So this is just they have shifted the energy scale to this energies, but essentially in the bang on in the blue solid line. So we are also confused about that while we are looking at it. Okay, so what I am saying is that direct detection can measure at this energy scale, and also at bonus you will be getting some points over there. So essentially what we are doing this measurement through neutrinos, again through solar neutrinos. As I said, these experiments can measure what is nuclear recoil and what is electron recoil, and essentially if you have neutrino electron interaction, that would going to appear in this electron recoil channel, and if you have neutrino nuclear interaction, that is going to appear definitely over this nuclear recoil channel, but the contamination at H2 only analysis from the coherent neutrino nuclear scattering would be larger compared to neutrino electron scattering. That is just because the cross section is larger. So in the H2 only analysis, the contribution from the coherent neutrino nuclear scattering will be larger. And I am only talking about experiments which are big enough to detect current neutrino, like neutrino events from the sun. So that's like XENONNT or PandaX or Lux Delta. See, I have not received them, but they are detecting some.
So can I go back to the motivation? Okay, regardless of the plot. So you want to look at
So we believe in.
at Q of 10 to the minus 4.
Hmm.
I see, and that you should be able to predict from the running of
Standard one.
running of standard.
Right. Yeah.
I see. Okay.
So
you want
given
to-
this, we just want to have a test of this. We are not saying standard model is not true.
Yeah.
We
So
believe in
this is
standard
what I
model.
mean. You want
Yeah.
to-
So we just want to have.
demonstrating is not there at
Yeah.
that point. This one is there.
Okay, so now is the question: are our experiments detecting something? So yes, we are detecting something. Recently, XENONNT and PandaX has detected 8B solar neutrino event using their experiments, and while this XENONNT has only did this S1:2 analysis, I mean they only focuses on the nuclear recoil scattering. Both of them are focuses on the nuclear recoil scattering, but XENONNT has only done S1:2 analysis, but PandaX both did S1:2 and S2 only analysis. With the S1:2 analysis, XENONNT has detected around 11 events, and PandaX has detected around 3.5 from S1:2 analysis, and with the S2 analysis is around 78. So the statistical significance is around 2.7 sigma. So essentially we are observing a standard model event. Can you say something new about standard model? So what we are essentially trying to do is, given a solar neutrino flux, the number of events that you are detecting in your experiment, so depends on what is the value of the sin square theta w, because your differential cross section depends on what is the sin square theta w is. So depending on sin square theta w, the number of events that you are going to observe is going to change. That essentially we utilize. So essentially the number of events that you are detecting in your experiment can be utilized to sort of determine the sin square theta w. We again did some likelihood analysis, and here is the profile for.
But you need to know the neutrino-nucleon cross-section.
That is determined essentially by this factor and GF. GF we assume to be.
Okay, so I'm taking GF out,
Mm.
apart from GF, I mean that cross-section should have, I mean you need to know how to calculate that cross-section from.
It's from the standard model itself.
Just calculate.
No, but there will be form factors from the nucleon itself.
So right. So the recoil energy regime that these experiments are currently operated, or the result reported, there it's really flat. Probably
So you don't have any
form factor dependence. Like probably 0.97 or something like that.
There has been some recent measurements of these cross sections, right? Calculated measurements
From the coherent that you were saying.
coherent or something.
Yeah, that is using some different target. Here we are using, let's say, general
Cosinus also measured it.
cosine. Yeah, cosine is.
Not cosinus.
Which one is this?
The one in Germany.
Oh, okay, okay. Yeah, they
They have measured it 1 month or 2 months.
yeah, right. They have recently. The previous result is probably.
Coherent.
uh,
Similar science, the measurement of sin square theta is coherent part of the data.
sorry.
As coherent try to constrain sin square theta.
Right. There are. I am going to show you that. Okay. Now, so here is the plot for chi-square profile for XENONNT and PandaX. Red solid line is from PandaX, and the magenta line is from XENONNT. And once you have, as you can see, the standard model expectation itself given by this black dashed line, and it's sort of in the middle of the what you are getting. So it's sort of consistent with standard model itself. And given this, you can sort of follow this kind of chi-square profile and calculate what could be the value of sin square theta w at 1 sigma. That's what we try to do. And here again, sin square theta w is plotted against the energy scale. So these two are sort of a measurement from PandaX and XENONNT. Essentially, while the recoil energy that you are operating is above 1 keV or so, but what you are trying to do over here is the energy scale of the operation is essentially fixed by where the momentum transfer is happening. So you essentially what you are trying to do is you are trying to scatter the xenon nucleus from a neutrinos, and xenon has a mass of 122 GeV. Now, to push a 120 GeV nucleus to 1 keV energy, you need this much amount of momentum transfer. So that sort of fixes the energy scale of the measurement. Now that means you need to have larger momentum transfer so that you can push a heavy nucleus. So if you use a lighter target, then perhaps you can measure this particular parameter even in the lower energy scale. That sort of prompts us to think that we can use probably neutrino electron scattering to measure this particular parameter even at the lowest energy scale. So then we try to do that again. As I said, your experiment is capable enough to separating between what is nuclear recoil, what is electron recoil in certain recoil energy regime, and we have tried to utilize that. Utilizing neutrino electron scattering events, we have tried to measure again the sin square theta w. But the point is that with neutrino electron scattering, these experiments are detecting almost 60 events, but these are not statistically significant enough just because electron recoil always comes with huge background. These are just coming from, let's say, radioactivity. So lead, krypton, these are producing huge backgrounds of electron recoil. So that sort of kept us, even if we are detecting 60 events, that is not statistically significant. Still, we have used this particular XENONNT electron recoil result, and here is our sort of chi-square profile for that. The blue solid line is what we are getting from our numerical simulation, and as you could see, above 1.16 sigma, you could only get upper limit on the sin square theta w. You just cannot get any measurement just because your measurement is not good enough. So it's sort of background dominated, other background dominated. And at 1 sigma code.
PandaX in their table they have this measurement. Not measurement,
Right.
they have this contribution.
Yeah. I mean, the most sensitive one is the XENONNT one. I mean, they probably understand their background best. even if you use, let's say, PandaX or Lux-Zeppelin result, you are always going to get some upper limit on the flux. You are not going to, at 1 sigma, you are not going to get any measurement. So this is because of some background, I think. I'm forgetting which background it is, but this just because of background. It's probably one of the krypton or something like that. No, probably something else. Okay. So then we have tried to do it in 1 sigma, and this is what our plot looks like. Again, this is at the energy scale, probably orders of magnitude smaller than atomic parity violation measurement, but our error bar is quite huge compared to atomic parity violation experiment, just because we do not have statistically good enough data. So essentially here again you are recoiling electron to 1 keV, and the corresponding required momentum transfer is required to have around sub-MeV regime, and that sort of sets the energy scale of our measurement. So it's not only about the measurement, it's also about the energy scale where you are doing the measurement. Since these experiments are probably the best experiments in this energy scale, that's why they could do it. So with this, I'd probably like to conclude. I have discussed that neutrinos is one case, be a problematic to dark matter searches, and I have sort of defined the cross section below which neutrino would become an important background for sub-GeV dark matter electron scattering. And given that you can detect these neutrinos in your experiments, we sort of said that you can measure a standard model parameter, perhaps at the lowest energy scale utilizing neutrino electron scattering. And there are huge scope of improvement with these kinds of future things. So XLZ, I have not mentioned probably the crucial one, which is PandaX-4T experiment, which they have already started building. Yeah. So they would probably be decrease this flux by probably significant amount, and you will have more precise measurement over here. And in between, you could have some measurement from dark side, even with, let's say, other combined dynamic and sensor is going to combine to oscura. They will also probably see some core and neutrino nuclear scattering events, since being probably the lowest threshold. They're also going to measure these things in this energy scale. So with that hope, I'd like to conclude and take any question if you have. You can also email me.
Thanks, Tarak, for the excellent talk. Are there questions? I can answer.
Miss, what is your theory talk? What is the motivation for that? No,
So,
that band that
right, I'm going to that. So, I mean, there is no new physics motivation for that. It is just, let's say, for this one, for the upper one, it is a scalar dark matter talking to standard model through a dark photon. Now you can tune around dark photon masses so that you can get this particular relic density a lot of time. And this is for something else where elastic scattering is setting the dark matter abundance, the lower one. So it essentially the combination of 3 to 2 and elastic scattering. I can explain to you later also. So this is sort of an popular models that could produce the observed relic density for dark matter.
At those masses, it's hard to get the right rate.
That is just, I mean, if you have a heavier mediator, typically those do not produce the correct relic one. And that's what famously Weinberg bound on the dark matter masses. Yeah.
These are very specific scenarios which you can actually.
There are nowadays there are various different mechanisms through which you can. Yeah.
There's no prospect for improving on silicon, right? There's nothing lighter that can be realistically used as a target. So
Using EDM.
well, in principle, but in
No, I
practice,
think they are in R&D.
with enough mass, that's the question.
See, here you don't need enough mass. Here the mass can be small, you can still do it.
The eye is small, but not the actual
But
mass
to
of the
me,
detector is
it's really been like
substantial.
any dark matter masses which is below MeV and which has a sufficient cross section with standard model is probably be ruled out by BV and CMB. So that's sort of been one of the important point that I don't know. I mean, people nowadays doing all these condensed matter target to search for even dark matter masses which is below MeV, but usually they probe the cross section which perhaps not be consistent with the data, but there is no sort of consistent study which could do that, which could sort of show you that these are not consistent with BV and CMB. So even for this particular plot below 1 MeV, I probably do not believe in anything.
Well, some of those bounds require energy dissipation. So if it was asymmetric, you don't have that.
Even if you have the scattering, then dark matter will thermalize
Sure.
during the BB and CMB time, and
That's a much smaller energy deposit than annihilation.
right. But if it is thermal, then it's ruled out.
If it is thermal, yes, but it could be non-thermal as
Then it's all right. That's all
just
right.
as we are.
Right.
It is not
Right.
particularly
Right.
exotic.
Right. That I agree with you.
I have a question. So have people used neutron experiments to detect lots?
Oh yeah. I missed you.
They finally thought that that will be clear.
Yeah.
So
So
none of them are neutron experiments.
no. This one is, I think this one is from coherent.
No. Sorry. By neutron experiment, I mean superatomic conductivity.
No. So like Borexino,
Yeah.
and you can use that. In principle, Borexino could be a useful probe in this range
Yeah.
because that has lowest threshold compared to, let's say, coherent and others. And that is not only that. That is using neutrino electron scattering.
Yes, that's really
Yeah. So that could prove over
And
here.
there the form factor is not equal.
Right.
It's just
Yes.
it's not-
Yeah, right.
So all that answer will be equal.
So there could be some measurement over here too.
So for this cycle period plot, so is the uncertainty like simply coming from the
Measurement.
base number of events that you have? So for example, if we see the same number of events, this is key percentage experiment or this silicon hypothesis. So will we have the same sort of error bars in the
So here error bar is just statistical error, like whatever experiment background error bar. Now if you decrease that error bar, the error bar of our measurement is going to decrease. Now depending on if you are talking about energy scale of the measurement, that is essentially fixed by the recoil energy that you are operating. Now skipper CCD could do the recoil probably smaller than this one, and then they could probably go to the lower regime. But the problem is skipper CCD, they could not separate out electron and nuclear recoil below about 100 keV or so. So that's been very difficult to do. So but this experiment could do it at about 1 keV or so. To the best of my knowledge, this is around 100 keV or so. Right. Mm-hmm. For Borexino, I don't think so. Borexino you cannot.
so when people talk about using super neutrinos, neutrinos, hitting protons is a switching factor related to the light beam and
That is UV bar. That is UV bar. UV bar. Inverse filter.
Yeah.
Here
I'm
is
not talking about in the period.
Yeah, I know.
I'm literally talking about not coherent but elastic scattering
Proton.
on protons.
Proton is very heavy actually.
That I don't know.
Despite that.
Okay.
That I don't.
Okay.
We can talk. So this is with snow plus and Borexino.
Yeah, there is no.
You can hit the neutron
Take it.
and yes, exactly.
No, when I said super K, I mean all of them.
Yeah.
Just one name. I have one more question. Sorry. Sorry. So when you draw this line, effectively you are also measuring the solar neutron like this. When you draw the uncertainty, are you taking the solar neutrino flux
Uncertainty in the
from the theory, or are you taking it because technically it's not science
Here.
square, it's science square times the flux. In
right,
some sense.
right. So
what
now for the 8B solar neutrinos, it happens to be the measurement is the giving you the best uncertainty.
Which measure?
The I think it's combination of super K
Okay, good.
and Borexino. I
It's
believe.
completely measured.
No, no,
Yeah.
I think is the uncertainty I'm using the measurement
See,
of this-
experimental uncertainty.
Take this experiment or the super neutrino?
Super neutrino
Neutrino.
experiment.
Okay, that's it. You're using neutrino experiment.
And theoretical uncertainty is larger.
Yeah, that's fine. Okay, are there other questions? Okay, if not, let's thank Tarak again. Tarak is here till Wednesday.